Well, Rwanda, thank you very much for your generous and kind introduction. It's my great pleasure to be here today. It's my first visit to Tacoma, and I find that, of course, I didn't have a chance to look around, but whatever I saw, I liked. And I think that I'm in a very friendly environment here. So today I would like to talk about this particular subject, NL computation. Now, if you would like to have my presentation, perhaps you could get it from here, or else perhaps you could send me an email message, zadeh@eecs.berkeley.edu, and I'll be very pleased to send it to you. Now, the reason why I say that is because I'll have many more view graphs than I will be able to present here. See, that's the sort of an approach that I use now. I skip skip a lot of detail with the understanding that if somebody is interested, then you can get it. You can. Now, I don't know if my microphone works or not.
I can help that.
Yes.
Is it working okay? You guys see it all the way back there?
I think this might be a little bit better. Yes. Thank you so much. Thank you so much. So, what is NL computation? The basic idea is this, that when we compute, we usually compute with values of variables. Now, in NL computation, you take a sort of a general view that what you have to compute with are not values of variables, but information about values of variables. So it is a little bit more general than conventional computation. So let's take a look at this sort of a basic problem. I have a function of x and y, and I know the value of x, I know the value of y, and compute the value of z. No problem. Now, suppose that, as I said a moment ago, I can't see too well from here, so I will move here. Yes. So you have some information about the values of x. Let's call it NLX. Information about x described in natural language. And then I ask you then, what will be the value of z? Now, there are many real-world situations in which this is really the case. You have, and this is an example, what is the difference between the ages of Vera and Pat? Now, I have some information about Vera and Pat. Vera has a son in mid-20s and daughter in mid-30s, and Pat has been in practice for so many years, and so forth and so forth. So the question then is this: how can you come up with an answer to this question? Now, the reason why I call it new frontier in computation, because you will not find methods of solving problems like that in the literature. In other words, the problem is how to take something that is described in a natural language and convert it into something they can compute with. That's the problem. Now, there has been a lot of controversy surrounding fuzzy logic, and many people don't like the word fuzzy. Bush sometimes uses it in arguments with other people, accuses them of using fuzzy arithmetic, yes. And because fuzzy is not a good word, basically. So anyway, so controversy, can you do something with fuzzy logic that you cannot do with other methods, in particular with probability theory? So I say, no, you can't. Now, of course, people disagree with me. I'm prepared to argue. Now, the way I argue about it is simple. I give a problem. I say, you tell me that whatever I can do with fuzzy logic, you can do with something. Well, go ahead, solve this problem. Now, if that problem is solved, I raise the bar a little bit until the person that I argue with surrenders, says, I'm sorry, I must admit that I cannot solve the problem. So, okay, so here is an example. Y is a function of x. Now I describe x, function of the function f, in the form of what I called fuzzy if-then rules. If x is small, then y is small. If x is medium, then y is large. If x is large, then y is small. And then I say that usually x is medium. What is z? Now, this is one of those problems. When I argue with my friends in probability theory, I say, solve this problem. You see? How do you solve it? Well, when you take a course in probability theory, nobody teaches you how to solve problems like that. So, well, some more examples. Now, I'm not going to go through all of them, but perhaps just a few. Now, here is one. Overeating causes obesity. Obesity and overeating cause high blood pressure. I overeat. What is the probability that I will develop high blood pressure? I ask questions about probabilities, but how to use probability theory to come up with answers to problems like that. Okay. So there are many more problems, but these problems are intended to give you a rough idea what is NL computation. Now, as I said earlier, there are many problems in real-world situations in which this is indeed the case. But as you will see a little bit later, people do not really use right approaches when they try to solve problems of this kind. So, so what is the problem? The problem is this. Natural languages are intrinsically imprecise. And imprecision of natural languages is rooted in the fact that a natural language is basically a system for describing perceptions. That's really what a natural language is. But perceptions are intrinsically imprecise. When I look at somebody, I have a perception of this person's age, height, weight, whatever, but I cannot describe the values that are involved in numerical form. I cannot say that person's age is 23 or whatever. I can't. I can guess. So I express it in natural language. I say young, I can say tall, fat, whatever. I use a certain system, which is natural language. But the values are imprecise. And it is this imprecision that creates problems. So we differentiate then between measurement-based information and precision-based information. So some examples. So on this side, we have perception-based. Here we have measurement-based. It's hard to find parking near the campus and so forth. So this would be perception-based information. Now, so NL capability then is the capability to compute with information described in natural language. And what happens then is this. If you look at various fields of science, you find that in general, scientific theories do not have this capability. And that is why I call this thing a new frontier. You don't have it in probability theory, you don't have it in physics, you don't have it in any field, in economics and so forth. You don't have it. Now, so there's a historical note. The point of departure is my 1973 paper, Outline of a New Approach to the Analysis of Complex Systems and Decision Processes. Now, in this paper, I introduced two concepts. One was the concept of a linguistic variable, and the other was the concept of fuzzy if-then rules. Now, my first paper on fuzzy sets appeared in '65, so that was 8 years later. Now, if you look at the applications of fuzzy logic today, you will find that most of them use these two concepts, the concept of linguistic variable and the concept of fuzzy if-then rule. Now, so linguistic variable. So linguistic variable then is inspired by the way humans deal with the implication of perceptions. So for example, age, if you don't know the age, you say young, middle-aged, old, whatever the case might be. So here then are the values of age, and here the values of honesty and so forth. So linguistic variable then has this some kind of a flavor, and it uses what I call sort of primitive terms like young, middle-aged, old, together with a system of hedges, not very young, extremely young, somewhat young. That's what people use. So instead of using conventional measurement system, 1 meter, 2 meters, 3 meters, 4 meters, and so forth, you use these basic or primary terms, and then you modify them, very young and so forth. So this is the concept of a linguistic variable in brief. Now, around the concept of a linguistic variable, then you have fuzzy if-then rules. Now, if-then rules have been in existence for a long time, but fuzzy if-then rules were introduced in that paper. So if something is small and something else is large and something else is whatever, then something else, something. So you assign linguistic values to variables, and you have these rules, and you have a rule set. So you don't have just one rule, you have a rule set. And these rule sets then are used in most of the applications of fuzzy logic. Here's an example, Honda fuzzy logic transmission. Most Japanese cars use fuzzy logic transmissions. Volkswagen uses fuzzy logic transmission, and many other cars use fuzzy logic transmission. In the United States, so far as I know, only Saturn uses fuzzy logic transmission. So this is an example. So what happens then, you have rules like this. I'm not sure where the, okay, fine. Okay, so you have rules like this. Now, notice one thing, that you use terms like low, very low, something. So, okay, what's the meaning of these things? Well, the designer of the transmission has to calibrate them. And these are so-called membership functions. What it means is this. You say, if the numerical value of some variable is something here, now at this point it doesn't work too well, unfortunately, then the degree to which it fits the description low is such and such, you see? That's what the designer of the fuzzy logic transmission does. So when you say young, middle-aged, old, some people say, oh, well, these terms are context dependent. Sure they are. But if you say young, then I have the right to ask you to tell me, what do you mean by young? And you define that by saying, if somebody is 25, then to me that person is young to the degree 0.8. And if somebody is 35, to the degree 0.1 and so forth. Having done so, then you have defined quantitatively what do you mean by young. So that's the basic idea. So as you can see then, it is inspired by the way in which humans use natural language to describe values of variables. Now, when I described these ideas initially, there was a lot of hostility, resentment, criticism, and so forth. Now, but it turned out that these ideas were simple and yet important. Now, here are some statistics about fuzzy logic, still controversial. You see the numbers here. This is the number of papers and books with fuzzy in title, not in the text, not in the abstract, not keyword, just in the title. And so you see now inspect database, which has to do with engineering, physics, it has over 50,000. But interestingly enough, in the mathematical literature, and in mathematics, fuzzy is not a very fashionable world, there's still about 15,000 papers with fuzzy in title. And these are papers reviewed in math reviews. So, so you see that there is something that we are moving in the direction of mimicking the way humans deal with certain things. And that turns out to be the right direction, even though initially it may be the wrong direction. Now, my good friend Rudy Kalman, many of you are familiar with Kalman filtering. Now, I was making a presentation in France, 1972. That was my first presentation. And at the end, there was not supposed to be a discussion, but he waved his hand like that. The chair recognized him, and so he got up and said something that was much more, let us say, derisive than what you see here. This was sanitized version of what that appears in discussion. But what he said, he said something like this. He said that if Professor Zadeh gave that kind of a talk in the United States, he would be lynched. This is the word that he used. He would be lynched. Okay, well, I have some scars on my back, but now, okay, there were many comments. I could actually talk for the whole hour about this sort of a thing. My good friend, my colleague, Khan, and I say good friend, I really mean good friend. But we disagree when it comes to this. Now, that's why I say fuzzy logic is wrong, and pernicious, something. Now, people who hold strong opinions like that, without exception, know nothing about fuzzy logic. I have yet to run into a person who says things like that, and then I ask that person or somebody else, can you tell me what fuzzy logic is? He said, I don't know really. In other words, people develop this kind of hostility, not knowing what is it. So anyway, but you know, I've never been bothered by this sort of thing. And my suggestion to you is this: no matter what nasty thing somebody tells you, respond by saying, I'll take it as a compliment. That's a very useful sort of thing. So anyway, so so what my critics did not really appreciate it is this: that what is involved is a gambit. Now, you know, chess, you sacrifice a piece to gain some advantage. I call it fuzzy logic gambit. And so there are some people who object to the word fuzzy, but there are other people who object to something else. They object to the fact that in the case of fuzzy logic, you sacrifice precision. You see? You use words, you see, rather than numbers. And they don't like that because science has been moving in the direction of greater precision, moving from words to numbers. That has been equated to scientific progress. All of a sudden, some say, let's move backwards. Well, people don't appreciate that. Now, so let me then, explain what that gambit is. But first, I have to clarify what is meant by precision. So I'm going to differentiate between precision in value and precision in meaning, or for short, V precision and M precision. Okay? Now, something can be V imprecise and M precise. For example, if I say that something lies in a certain interval, I'm not giving you an exact value of that variable, but you know what I mean. The meaning is precise. When I say that something is a Gaussian random variable with certain mean and certain variance, I'm not telling you exactly what the value is, but you know what I mean. So this is what we call imprecision. Now, so furthermore, we have to differentiate between the kind of precision which is oriented toward humans, MH precision, and MM precision. So if I ask you, what do you mean by causal dependence, you can describe it the way a dictionary would describe it, or you can describe it in mathematical form. So if you describe it in mathematical form, then I'd say it's MM precision. And if you describe it in the way dictionary does it, then this would be MH precision. Now, so what is the fuzzy logic gambit? Roughly it is this. I know exactly when Lily was born. Somebody asks me, how old is it? I say young, you see? Instead of saying, well, she is 23 years and 6 months and 2 days and 13 hours and 22 minutes, I say young. Why do I do that? That may be good enough, you see? Good enough. So precision carries a cost, always. So when you move in the direction of imprecision, you sacrifice something, which is precision, but you gain something too. You gain cost, simpler. See? When you use data compression, you do the same thing. You sacrifice faithfulness, accuracy, whatever, but you reduce cost, smaller bandwidth, whatever. So what happens is this. So I say she is young, but then you ask me, what do you mean by young? Well, I preciate it by saying young is a fuzzy set. That is the membership function of young. This means that if I gave you a numerical value of age, I would be able to tell you what is the degree to which that numerical value of age fits the label young. So what have I done? I sacrificed precision here in moving from here to here, but then I followed it with making precise what is the imprecise thing that I said. That's the gambit. See? So in most applications of fuzzy logic, this is what is used. Now, this is a little bit of a surprise in the sense that when I wrote my first paper, I thought that fuzzy sets would be used in those applications in which things were not precise, like philosophy, like psychology, like sociology, like economics, and so forth. But then it turned out that today most of the applications of fuzzy logic relate to situations in which you know what the precise values are. You see, it's a little surprising. So you impreciate, but this imprecision is deliberate. It is not forced on you. And so when we talk about imprecision, then as I said a moment ago, there is something that you're forced to do because you simply don't know what the value is, and something that you do deliberately. And that's the fuzzy logic gambit. Now, so okay. So when we use NL computation, then that is what happens. We, instead of using numerical values, we use values described in natural language. And there are two rationales. One is we don't know really what the value is. And the other one, we know what the value is, but we choose to describe the value in natural language. And that's, as I said, a little surprise. And that is why, in many cases, fuzzy logic is misunderstood. Because what's not realized, that you do it deliberately. Okay, now, so what it boils down to then is that you have to preciate natural language. Now, how do you do that? Now, you cannot precision natural language using two-valid logic. Now, linguistic theories today are based on two-valid logic. In mainstream linguistic theories, everything is two-valued. Either something is grammatical or it's not grammatical. And in classical logic, either something is true or it's not true. Either something is ambiguous or it's not ambiguous, and so forth. I say this is wrong. In natural languages, this is not the case. Everything or almost everything is a matter of degree. Grammaticality is a matter of degree. Something can be more grammatical, more ungrammatical, and so forth. Ambiguity is a matter of degree. It can be slightly ambiguous, could be highly ambiguous, and so forth. You see, that's the way it is. And in particular, when it comes to truth, it need not be completely true or completely false. It could be somewhere in between. Okay? Now, this in-betweenness of truth, of course, has been recognized for a long time, multi-valid logic and so forth, but fuzzy logic moves far beyond that. So there is this misconception that fuzzy logic is multi-valid logic. No, fuzzy logic goes far beyond it, because in fuzzy logic, everything is allowed to be a matter of degree, and not just truth. Everything, you see, is allowed to be a matter of degree. Or so it is or is allowed to be a matter of degree. Now, so let us focus our attention on precision then. Now, a little bit of terminology. Now, these are words that I try not to use new words, but once in a while I have to. So precision is the object of precision, and precision is the result of precision. So we concern ourselves then with precision of natural language. Now here we start with a simple example. I say approximately A. Then you ask, what do you mean by that? I want to preciate it. Well, things can be preciated many different ways. For example, approximately A, you say, is A. Approximately 5 is 5. Or you can say approximately A is an interval. And what interval? Well, that's a matter of context dependence. If I say he is approximately 23 years old, you see, then you say, what do you mean by that? You say 23 plus minus something, you see. What plus minus what? Well, context dependence. But you have to specify that. When you preciate, you have to specify 23 plus minus what? Or it can be fuzzy interval, in which case then the boundaries are not sharp, or it can be some other things. So basically, the point of view that I take is that we deal with models of meaning. So when we construct models of something, economics, whatever, we take something that is imprecise to begin with, but we construct a precise model, mathematical model, some other model. Now, that model may be a good model, may be a bad model, but it is a model, you see? It is a model. So we can talk about models of meaning. So when we preciate, the precision end, what we wind up with, is a model of meaning. That's the position that we are going to take. Now, so let's take an example. I use many examples. I'm a great believer in examples. So I say overeating causes obesity. You ask me, what do you mean by that? Now, MH precision. I say, what I mean by that is that most of those who overeat become obese. Now, this is not MM precision. A little bit later, I come up with MM precision. For the present, I'm going to skip that. So this will be then MM precision, and what you see there is MH precision. Now, interestingly enough, what happens is this, that if you take that example that I showed earlier, and you ask the question, what is the probability that I'll develop high blood pressure? The answer is most squared. So we are dealing then with an arithmetic in which you can square words like most, whatever, most squared. Now it depends on how you define most, how do you calibrate most. But whatever it is, it will be most squared. So what happens then is this. Even though we use things like obesity, overeating, and all sorts of things, the answer does not really depend on that. Depends only on how do you define most. This is a characteristic of computation with information described in natural language. What you see, we are using deep structure, proto-form. We are not using surface structure like overeating causes obesity and so forth. We construct deep structure of that, and we compute with deep structure. Now, so this is what I said already. So this is the fuzzy logic gambit that I talked about already. So here is then the basic structure of ML computations. First, we have to precision. And we don't precision necessarily one step. It may take a few steps. Now, once we precision, then we can compute. But in the approach that I'm going to describe, we are going to stop at this point over here. The pointer were a little bit better than we could see it better. So at the point where you say, now I have reduced this problem to something that is a standard mathematical problem. I'm not going to push it beyond that, because then you say, okay, you're on familiar ground. You know how to handle problems like that. So when we talk about solutions to various problems, you have to recognize that that's what I'll be doing. Now, now there is a fundamental thesis, which is that information is a generalized constraint. Now, I haven't defined what I mean by generalized constraint. I'll do that. But roughly speaking, constraint is something where you restrict a value of a variable. Generalized constraint is some general way of doing that. So when I tell you something, I am restricting the values of a variable. So if I say Martine is young, I am restricting the values of her age, but I'm not pinpointing. I'm not saying that she is so many years old, you see. So in a natural language, these constraints are generalized constraints. You say so-and-so is honest, you are constraining something. So the fundamental thesis is that information is a generalized constraint. It is not the way information is defined in information theory, whether it's defined in statistical terms, in terms of entropy and so forth. That definition is a special case of the definition that I use here. Now, a proposition is a carrier of information. So it follows then that the meaning of a proposition is a generalized constraint. And so the concept generalized constraint then is the centerpiece of NL computation. So we compute then by taking something that's described in the natural language, converting it as a generalized constraint, and then computing with generalized constraints. And that is why conventional techniques cannot handle these problems, because the concept of precision is not there, the generalized constraint is not there, these constraints are not there. And without these concepts, you cannot do it. Now, incidentally, when I was talking approximately A, there is one point that I did not make, I should have made, and that's this. I said the simplest way of describing what you mean by approximately A is to say it's A. This is what's used in most scientific theories, particularly in probability theory. Most real-world probabilities are not known precisely. So when you say probability of something is 0.7, you don't mean 0.7000000, but that is what you use in computations. So when you compute with imprecise probabilities, then you generally interpret this description, like 0.7, as an exact number. And the same happens when you deal with losses, when you deal with other things. They are approximate, but you treat them as if they were exact numbers. I was talking to a student in Berkeley. She took a course on decision analysis, and she showed me the volume. Everything in that volume was based on the assumption that you know exactly the values of probability, exactly the values of losses and gains and so forth. I told you know what? You're not going to use really all the things that are in this book in real life situations. I mean, we'll use it, but the answers will not be really realistic answers. So from this point on, I'm going to skip more and more view graphs, so please accept my apology for doing so. Okay. So NL computation is based on fuzzy logic. Now, there are many misconceptions about fuzzy logic. Fuzzy logic is not fuzzy logic. It is not fuzzy, it's precise logic. It's precise logic of imprecision. And there are two things in fuzzy logic that are of primary importance. One is the concept of graduation, meaning assigning degrees, not graduation in the academic sense. And the other one is granulation. These are the two characteristics of fuzzy logic that differentiate fuzzy logic from other disciplines, other techniques. You don't do that in probability theory. You don't use graduation, and you don't use granulation. Now, so a way of looking at it is this, that in fuzzy logic, you write not with a ballpoint pen, but with a spray can. That's what you write with. So if you have a curve, a function, you don't draw it with a ballpoint pen. You draw it with a spray can. But you can ask the question, what is the maximum value of this sort of a thing? And people will say, well, it is something like what you see here. What you see here, you say that is the, I don't know. Well, anyway, I have to give up on that. You see that little red thing, I mean, the circle there, that will be the maximum value. Now, how do humans do that? I may have to skip view graphs in which I explain in greater detail how is it that humans arrive at that kind of an answer. But within fuzzy logic then, you can deal with this problem both imprecisely and precisely. In other words, you can compute exactly what the maximum value is given this imprecise information. Now, so what you do then is this. You take a function and you express this function in natural language. To do so, you granulate x and you granulate y. So what you see there is small, medium, large. These are fuzzy sets. Those triangles that you see there are triangular membership functions. So this is granulation of those two scales. And then you say if x is small, then y is small. If x is medium, y is large. And if x is large, then y is small. Now, this description could be viewed as a summary of the function. It's not an approximation, really. It's summary, summarization of functions. When you talk about summarization, ordinarily we mean summarizing a story, summarizing an article, summarizing something, but we can apply the concept of summarization to functions. This is how we summarize using natural language. Now, so now I mentioned earlier that when you precision something, the precision is a model of meaning. But we have good models, we have bad models. So the concept of co-intention is intended to tell you something about it. So if you say a precision is co-intensive, you mean that it's a good model. And so, when you talk about precision, then what we want is co-intensive precision. For example, when you're talking about approximately A, if you say approximately A is A, that may not really be a good model. So, now what happens is this, that in scientific theories, we use, for the most part, bivalent logic. And we define various concepts as bivalent concepts, either true, not true. Either it fits it or doesn't fit it. But in reality, these concepts are not really bivalent. They're fuzzy concepts. Stability is a fuzzy concept. So to come up with co-intensive precision, you cannot use bivalent logic. So when you describe something in natural language, and when you subsequently appreciate that, we are trying to come up with co-intensive precision. That's what we try to do. Now, so I mentioned earlier generalized constraint. So what is it? Well, generalized constraint is something like the following. You have a variable x, which is what we are constraining. We have a variable or a relation r, which constrains x, and we have little r, which is an indexical variable, and that the value of that variable tells you how r, capital R, constrains x. So we allow for a large variety of constraints. That's essentially what we do. And so conventional constraints then, which are usually hard constraints then, would be a special case of this sort of a thing. So we assume that most real-world constraints are elastic constraints. And the question is, how do you characterize that elasticity? That's the question. That's the question. Now, checkout time is 1 p.m. That is an elastic constraint, even though it appears to be precisely described. Speed limit is so many miles per hour, so many kilometers per hour, has some elasticity, and so forth. So you find that most constraints, most real-world constraints, have some elasticity, but we usually treat them as if they were hard constraints. So there is quite a bit of discussion now of various constraints, and I'll skip most of these view graphs. As I said earlier, if you're interested, you can have my presentation. So there important constraints would be probabilistic constraints, possibilistic constraints, heuristic constraints, usuality constraint, fuzzy graph constraint, and so forth. Let me say a word about usuality constraint. So if I say x is small, this would be an example of what we call possibilistic constraint. You're telling what are the possible values of x. If you say usually x is small, then this is a usuality constraint. It's both possibilistic because you said small, but it's also usuality because you said usually x is small. So you have to be able to compute with constraints with information described in that fashion. Now, a problem that I'll just mention now of that kind is the following. I have a random variable x. What is the probability distribution of x? Now, instead of telling you it's such and such, I'm going to give you some information described in natural language. I'm going to say, well, what I know about x is this, that usually x is much larger than approximately 5. And usually it's much smaller than approximately 100. And then I ask, what is the expected value of x? You see? This is a probability theory. I've yet to meet somebody who is in probability theory who can come up with an answer to this question. There is discussion of it in the literature. So what we're going to do then is this. We are going to take these generalized constraints, we are going to combine them, we are going to modify them, we are going to qualify them, and so forth. And in that way, we are going to construct what is called generalized constraint language. It's a language of constraints. And so what we are going to do then is this. For example, if you want to precision what do you mean by speed limit is 100 kilometers per hour, then you use that language to describe, no, the language of fuzzy if-then rules is a subset of the generalized constraint language. So you may have something like what you see here. You know, if the speed is less than something, then the probability of getting a ticket is low, and star x means approximately x. And if it is something else, it's so much. So I'm using now fuzzy if-then rules. And I can make these rules complicated, I can make them simple, whatever. But you can see, I think, that using this kind of a language, I can come up with a definition of what is meant by speed limit is 100 kilometers per hour that is more realistic than when I say that, well, below 110, okay, above 110, you're in trouble, you see. That's simplistic. Too simplistic, it's not realistic. Okay, so we are going then to ask, okay, I'll say the question. Suppose that you have this constraint. How can you reason or how can you compute with the constraints? And one of the rules, deduction rules, principal deduction rules, were called extension principle. That extension principle appears in my first paper, 1965, but in that paper I did not call it extension principle. I called extension principle in a later paper, 1975 paper, and basically what it says is the following. It says if you have a variable and you constrain not the variable itself, but a function of that variable, and if you say that function is something, small, large, whatever the case might be, and if you ask a question, what will be the constraint on some other function of x? Then you can ask that question. And the answer depends on the solution of a variational problem. You have to maximize some expression subject to a constraint. Now, this is a standard mathematical problem. So when I use this principle then, once I have this sort of a thing, I don't go further. I don't try to solve it because that becomes something that we are familiar with. But this is intended to give you a rough idea as to what's involved. So I start with proposition, with information described in natural language. I precision that information by translating into generalized constraint language. And once I have these generalized constraints, then I propagate these generalized constraints. And the principal propagation rule is the extension principle. So if I say, I have these view graphs, but probably won't have time to show it to you, that most Swedes are tall. This is the information I give you. And the question is, what is the average height of Swedes, you see? Then I'm constraining something when I tell you most Swedes are tall. And that constraint propagates to the constraint on the average value. It's another function. Because the average value is a function of something. And when I say most Swedes are tall, I'm constraining some other function. You see? So what's involved is constraint propagation. Now but as I said earlier, we deal with these constraints not in surface form, but in protoform, as protoform, deep structure. So when I say most Swedes are tall, what I say that this is actually an instance of a situation in which you have a population, you have an attribute, you restrict the value of the attribute, and then you ask the question, what is the proportion of elements in the first population in relation to the population to start with? This is what you do. So that's a special case. And deduction rules are protoformal rules. They tell you how to propagate constraints given the protoforms, not given the original surface form. And this is what we need when we work with search. I'm a little bit of a critic of what goes on in that world. We have Google, of course, wonderful, miraculous things, but search engines today do not have deduction capability. They do not, they cannot do that sort of a thing, you see. And so what they have to do, they have to move in the direction of protoforms, deep structures. So when a search, when there is a query, you find the deep structure of the query, and then you look at the catalogs of deduction rules expressed in deep structure form, and then you find those rules that are applicable to the query, and then you come up and answer the query. That's the basic thing, and this is not what is done today. So these rules, so just to give you a rough example, this is a rule. I'm not going to talk about the details of this rule, but just to give you a little of a flavor of a rule that is used in come up with an answer to the question, what is the probability that I will develop high blood pressure if I overeat? Now, so basically then what we have to do is this. We have to construct what I call precision natural language. This precision natural language is like a dictionary with 3 entries. The first entry is a proposition in a natural language. The second entry is its MH precision, like in a dictionary. And the third entry is MM precision. So let me repeat again. You start with information natural language. You first precision it through going through MH precision. For example, stability. You want to precision. So you look up dictionary definition. But then you want to M precision. Then you go to Lyapunov's theory of stability, or the book on control. And what's the definition of stability in that book? That will be the third entry in this kind of a dictionary. So when we talk about precision natural language, this is the sort of dictionary that we need. And when we finally come up with MM precision, we also come up with a protoform of that expression. So to sum up what I said so far then, the reason why I call this a new frontier, because you see that it is a direction. It's not a standard direction. It's a direction in which you say that what I have to work with is information described in natural language. Now, if you have information described in numbers, fine, use it, go ahead, use existing techniques. So what I'm talking about are situations in which existing techniques don't work. This is what I'm talking about. Then you have to take those expressions described in natural language, you precision those descriptions, and then you transform them into protoforms. Then you have a catalog of rules of deduction, protoformal rules of deduction. You try to find within that catalog rules which apply to the particular item that you are dealing with, and then you use the rules of deduction, you come up with an answer, and then you retranslate into natural language. That's the basic procedure. So I will stop at this point, and thank you very much. Thank you very much. if I offended somebody, please accept my apology. But except for one thing, and that is this. You know, Brahms, the composer, had a very sharp tongue. And he was at a party, and he was leaving the party. As he was leaving the party, he said, if there is anybody in here whom I have not insulted, please accept my apology.